I think that may be the excuse of him not being here anymore.
But like in a cool, fun way.
No.
I mean, I messaged him a few days ago. He seemed like he was doing well.
Just had a walk. I don't want to be here this fine morning. Jesse had to walk 12 feet.
Jesse has the bike here.
Yes, the one.
He has the bike here, like a few miles.
Just a few miles. I've seen him like home. He lives out on the same street that I do. Some of them.
So a mile-ish. That's private information.
Live in Lee. And also
Hello, Zoom people, can you hear me?
okay, then congratulations.
Can we take a picture?
Yeah, definitely. Of this thing, yes, definitely. In general, not so much. Okay. Okay, plans for today. I played more with cuckoo hashing. I corrected the typo that was in the slides about cuckoo hashing. It's not in the material of the midterm, and I didn't find a friendly way to give the analysis of why it with high probability give us order 1 expected time. For the search of cuckoo, for the insert of cuckoo, and on the other hand, we all know that find and delete takes constant time, because for every key there are only 2 places that this key might be in. So cuckoo hashing, I'll tell you more than what I expected. And today we'll finish Rabin's algorithm for string matching, and maybe a few questions that I thought of chatting with you about. And I'll continue toward my office hours that are at 11 today. So if people want to stay and ask more questions, I'll be happy. And if not, we'll find time for review on the midterm. The question on the whiteboard. A few people prefer not to move the exam, but it's weak preference. I want to make sure that it's global preference, that everybody is happy. Happy is a strong word. That okay, does anybody have strong feelings about moving the exam to either Wednesday or to the following Monday? Yeah, okay, good. Just to give more time to prepare. Anybody else have strong feelings? Okay.
I like to keep it the same.
Okay, I think that's it's not, and it's not that I'm not tuning the difficulty of the exam to what to how much time we review the topic. So material for the exam, no, if we move it or if we don't, open addressing is there, obviously, that's stuff that lot of you know from 445, universal family of hash function. That's also covered, by the way, in 445, just here, that you fully understand the proofs and why the families that we created, namely the dot product, if we take care of all the parameters, why does it indeed a universal family? If you feel that the explanation was not, that you don't know it by heart, we can review again. Why does a perfect family behave the way it behaves? And then how are we using the perfect families to create, how are we using, universal families to create perfect hashing? Right. And Cuckoo and Rabin are not in the material for the meter. And of course, everything before it, closest pair, linear programming, skip list, are all in. Okay, Rabin. Quick overview of the problem. Also, people on Zoom, if you have any strong feelings one way or another, I'll be happy to hear about moving the exam. So, we want to find whether a window of a few characters, 2 characters in this case, does this window match a pattern? And the pattern here was to for example, B, and I want to ask, is there any place, any shifting at which the window includes exactly B? And naive algorithm would say consider all the possible shifts. What is hidden here is from S equals 0 until N, and minus N, but N is very small. N is the size of the pattern. The text was to be or not to be something long, you see over here, and we are trying all the shifting of the window. Once the window is at some place, we are checking all the letters one at a time and ask, do they match the pattern or not? And of course, this algorithm runs in worst case of M times N. M is the length of P, the length of the pattern, and N is the length of the text, the book, much, much longer. And of course, we want to use hashing, but the way that we are showing how exactly the devil is in the details. How exactly are we using the hashing in this case, and what do we make to make it work efficiently is extremely clever. Okay, so of course I want to hash every shift, what I see in the window, and I want to hash the pattern, obviously, and I'll ask, do they match as numbers or not? So how will I hash in an elegant way? I'll take the first character, multiply by 1, second multiply by 2, next multiply by 4, and the last one, here I'm looking at window in size 4 because 2 was too small. Window size 4, multiply each one, the ith character by 2 to the I, 2 to the I minus 1 actually, and sum them up. And that would be my first attempt in a hash value. Promo, that by itself will not be very efficient, but it will be a good start for improvement. So that was the answer for this particular shift. And as I am creating more shift, then let's see what happens when I move the window by 1 step. Moving the window by 1 step, going to the next S, saying most of the bits stay the same, except that the bits, when I'm going now from S equal 4 to S equal 5, you notice, by the way, that I now write the text from right to left instead of from left to right. And the reason that I'm doing it is to be consistent with the slide, and because I want the leftmost digit to be the most significant, as we are used when we write binary numbers. So the shift starts from right to left. It is I reverse the text and the pattern, obviously, but it doesn't matter. Okay, what is the same and what is different between these two windows? Most bits stay the same. both bits stay the same. When I move for a shift of 9, what happens here? These three bits are going to stay, but the number that they represent will be half its size. It's just shift to the right by 1. It's just like dividing by 2. I can, for the sake of good order, get rid of the 1 over here, but it's not a problem. I know what is this digit, obviously. And I need to add to this overall number, I need to add a new bit from the left side. It could be either 0 or 1. Each one of these bits here is just 0 or 1. You multiply by 2 to the I. That's just how you understand binary numbers. Make sense? So I'll just shift it. I'll get rid of the 1 over here. If there is 1, that is, I'll just subtract from the number that is represented here, 13 in this case. Why 13? Well, 1 times 1 plus 0 times 2 plus 1 times 4 plus 1 times 8. 13. Decrease 1 if there is 1. Subtract 1, sorry. And do a right shift. This divide by 2. And add to it, since this is 1, then you're adding to it 1 times 2 to the m. 2 to the m minus 1. It is whatever it takes to make it the leftmost, the most significant digit. Okay, note the notation. T of S So the notations are undeniably a bit confusing. T of S without the prime, there is a prime, a tag going to appear. T of S without the prime is just the number that you see for the shift S of 8, moving the window by 8 steps to the left. That's determines the shift. What is the number that I see right here? That's what I called T to the S, when I understand it as a binary number, of course. Okay, so that would be T to the S. And why do I insist on making it numbers instead of making it strings? Well, it's even before, I still didn't start with the hashing actually, but thinking about it as numbers, I want to say I have a pretty powerful computer in the last 40 years, and this powerful computer can take 2 computer words of 64 bits and compare them, if they are equal or not, in a constant time. Right? It doesn't need, everything is implemented in hardware. I don't need to write a loop that checks each bit at a time. If I keep it as a string, then to ask, is this a string that appears in the pattern? I need to check each character individually. I cannot just ask the operation of compare this to this, which your computer is happy to follow in a constant time. So that's the first motivation of expressing the number, expressing the string as a number. It doesn't have to be in base 2, but why not? You can have the work with 2 bases, but it's just easier to explain. In terms of efficiency, quite possibly it's not the most. Everybody understand what is T of S right now? So in this example, let's write the example. If I have 1, what is this now? 1, 1. That T of 8, because that's when the window is at the 8th place. T of 8 is equals to 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 2 to the power 0. just for consistency. But making it 13.
I have a question. Why do we call it the hash function?
It will come.
Oh,
It's an excellent question, and it is still not really the hashing. Matter of definition, but it's still not the hashing. Now, as we said, what is T of S plus 1? T of S plus 1, T of 9, T of 9 will take these 3 digits plus another digit that I don't remember. It was 1, I think. Yeah, I think let's decide that it's 1 because I will not be able to stop it in the right place. And yeah, let's decide that it's 1. So I take these 3 bits and add to it 1 new bit from the leftmost side. So what do I do with this part? Moving from here to here, I need to get rid of this 1 if there is 1. If it was 0, I didn't have to subtract everything. So subtract T of S plus 1 times 1, divide by 2, add, look at the bit that is just now added from the left. If it is 1, then you're adding it to T of S. That is, I look at T of 8, and I want to generate from it T of 9. Generate from T of S, I want to generate T of S plus 1. So if the new bit that is come from the left is 1, I'll add the value of 1 times 2 to the n minus 1. That was, if I have 4 bits, this number is the 8 that came from the left. Okay? Everybody's cool with this? That's just the formula, meaning it at a constant time. Supposedly in constant time, I can compute from T of S what is T of S plus 1. Remember what we are competing against. Naive algorithm runs in order m times n. What we want to get from it is n will be the dominant part, m is much larger, but we want to get linear time algorithm. Okay, everybody feels comfortable with this formula? And yeah, so three arithmetic operations. So it looks like I can compute the new value in constant time. All happy. And of course, after I take T of S, I'll ask is T of S equals to small p. What is small p? You can guess it's the number that represented by the string p. P was a pattern. Think about it as a binary string. It represents some number. So just to compute from for every s, compute T of S from T of S minus 1. It takes constant times, 3 arithmetic operations, and compare it if it fits the pattern or not. If yes, then you're reporting fit, and it looks like we are done. Or are we? Or who can argue what's the problem here? Either virtual people, real people. If anybody of you sees a bug, or it's yeah.
Comparing, how can we compare? We can compare it with like m times, or we can do it using hashing in constant time.
Well, so far, this was just a number. a value. P is just a value. I did just a binary representation of the pattern. These are two numbers. I called a compare operation.
Yeah,
Ask
so compare operation, if we do as a string, then we have to
check
time.
one, yes, but since it's a number, it looks
Yeah,
like
then we
it's
hash.
constant because we usually compare, and I don't need the hashing so far. I mean, I'll need the hashing, but first we need to express what the issue with this algorithm.
The value of ds may be exponentially large if m is
Excellent, excellent. If m is m bits number, I mean, let's ignore the issue from moving from a ASCII to moving to binary representation. I look at the bits individually of the ASCII character of the to be or not to be. This is, even if the pattern is just this one, you're talking about a string of, here it's only 60 on only 16 bits, 2 characters, but it's very easy to get more than 32 or 64, whatever your computer word is. But the number of bits in M might be way, way larger than one computer word. So the compare operation doesn't take constant time. Your language, depending which one, might complain when you try to multiply such a large number. You cannot even store it in a normal computer word, not even if it's long. You can use a floating point, but then it's not really the number, it's approximation, so that doesn't work. But it's still a very good start. Because from now on, where am I going? We will store I will not compare instead of we look at the two hash values of both these numbers, T of S and P, and I'll ask, is the hash values match? And if it's rare enough that it match, then I can say there is a chance of false positive, of course. There is a chance of false positive, obviously. The hash values are the same, but the keys, the hash values are the same, but the numbers are different. But I'll try to control the chance that this happens. So of course, in this algorithm, once I see that the hash function match, that the hash values match, I'll have to check if the strings actually match or not. I'll have to verify it. But the algorithm is efficient just if I'll say that the number of false positives will be small. Okay, so that's one challenge, but to control the number of false positives. And there is one challenge coming sooner, that is, if I don't really want to keep T of S, it takes too many computer words. I don't really want to multiply it by 2. As is, it takes too many computer words. It's a number, but it's a number doesn't make it something that I can stack into one computer word. So, as you noted, we need to perform each operation in constant time if we want linear algorithm, but it's usually doesn't work if the number of bits is more than 64. Okay. Here I just wrote in a lot of words that I can divide when I'm living over a finite field using a group. If I think about all the numbers modulo a prime, and it is a prime, then for every number, integer, between 1 and m, between 1 and m minus 1, it has an inverse. It has x minus 1. That is, literally I can perform division. That is, x minus 1, it means that I'll take x and I'll multiply by y. Modulo q, it will be 1. Quick example and refreshment, it's also good for the midterm, to remind you what the basic mechanisms that we used again and again. I think about some number a between 1 and 5. So a between 1 and between 1 and 5, because I want to work in modulo 5. And I'm looking at the number xa mod 5. 5 is a prime. Let's try all the numbers. Proof by example. Let's try all the numbers where x equal 1, 2, 3, 4, and 5, of course, which is 0. And let's decide that a equals 2 in our little example. And what happens? 1 times 2 ax mod 5. If x is 1, then it's in on inverse, nothing happens because of the modulo. And then 2x will be 2. 2 times 2 modulo m equals 4. 3 times 2 equals 6. Modulo 5 equals 1, meaning that the inverse of 2 is 3 and vice versa. And 4 times 2 is 8, modulo 5 give me 3. And of course 0 takes me to 0. So what am I trying to show you? Each one of the numbers, no matter what is a, each one of the numbers appears exactly 1, the numbers between 1 and 5. Meaning that no matter what is a, one of these numbers will be the inverse of a. A is 2, then in this case x, the inverse of a, will be when do I get 1? 3. And we actually used this lemma quite a few times when we talked about universality. Said, as long as we are leaving everything under a prime, or I'm only playing with numbers that are smaller than this prime, then this sequence of operations, well, This function by itself, by the way, I can make it a universal family of hash function, another hint for the meter. I can argue that all these numbers are different, and so on. Great. What does it tell me? It tells me that in the operation of creating a, oh, and I also want to remind you that we talked about this fact multiple times. If I have two numbers and I want to sum them and it's too large to my taste, I can take the first number, compute modulo q, and take the second number, compare modulo q, and of course do one modulo q at the end. But if I have a multiplication of a numbers, like in the case of dot product, we use this fact multiple times. So from now on, T prime of S, did I skip the definition? T prime of S, if I didn't write it, what will be my hash function? Very simple, deliberately very simple hash function. Age of X is nothing but X mod Q, and Q is a prime. And notations, Ts was a number, Ts was just the number 101, the string 110, etc. The binary number, the number that is represented, that I wrote it in binary, and T prime of S, the prime is just my shorthand to say that's age of T of S. Take this number and compute it modulo Q. And similarly, P prime, you guessed, it's just age of P. So P prime of S is just this binary number modulo Q. How can I generate from it T prime of S? I'll subtract from T prime of S, I'll subtract 1 or 0, depending on what is this bit, just as I did before the modulo. And now I need to divide it by 2. How can I divide it by 2 if I want to only work with integers? I'll multiply it by 2 to the minus 1 modulo Q. We said that 2 has an inverse, like any number here. It has an inverse, I'll call it 2 to the minus 1. So I'll multiply it by one number, which I will just compute once and I know what it is. But 2 to the minus 1 modulo Q. That's just a division. Now I need to add to it T to the S plus M plus 1, that is a new bit that is joining, times 2 to the M minus 1 being added. And I'm computing modulo Q of the whole thing, but I don't really want to keep this number, 2 to the M minus 1 by itself is already too large. It takes too many bits. It's not a computer word. I'll just add to it 2 to the M minus 1, just do immediately mod Q. And that's a number between 0 and Q. And oh, by the way, I'll make sure that Q is a small number. Small, like less than 64 bits. So I know what is this number. It's a constant. I know what is this number. It's a constant. I am looking at 2 bits, do this multiplication, all under modulo Q. Take one more modulo Q just to make sure, and we are all done. That concludes this part of the algorithm. From now on, I'm just looking for moments where T prime of S equal P prime. That's a hash function, they're equal, and if they are, I check character by character, do they meet or not. So this part of the algorithm is very simple, very straightforward. Questions about it? Everybody understand why it's only 64 bits that I'm using and not M bits? So that answers the question, why do I need the hash value? Okay. So, and the problems are, of course, false positive. It could be that the strings don't match, but the hashed values, denoted by the numbers with tags, with prime, the hash values do match. So we need to use a random prime. And there will be some rules about what is this random prime. And the way that we are going to use it is, well, to my taste, it's extremely cool. Okay, we will show that the probability of a false positive is small, so even when I'll say, similar to the linear programming, if you wish, even if I'll say some bad things happen, I mean, I'm always checking when I see that this equals this, then I need to do like the solved linear programming in 1D, or the rehash that we used in the closest pair. I'm spending a lot of time if bad things happen to check if there is really a match or it's not a match, but I want to argue that I don't need to match this part multiple times. Okay, so let's try to understand better what happens if I have false positive. False positive will mean that T of S, the number after shifting the window to the S place, shifting the window by S, this number shifted by S is different than P, because if the number before the hashing are equal, that definitely means that it is a match. It's a correct match. But false matching will be when these guys are different, yet when I'll add the primes here and here, they will be different. Modulo Q, they are different. So let's understand how it happens. So I know that both this number modulo Q that these numbers by themselves, before the modulo Q, these numbers lives between 0 and 2 to the m minus 1. Why? Because I just used m minus 1 bits. No much smarter about it. So, question, how many primes can you find such that T of S modulo Q equals P modulo Q? How many different primes Q could I find that will cause this false matching? But if Q of S modulo Q, which is different than P, is different than P modulo Q, that will imply that move P to the other side, subtract P from both sides. You can do it under modulo. T of S minus P is equal 0 modulo Q. How can I have a number equal 0 modulo Q? Why does it happen that 12 modulo Q, and I'll tell you that Q is prime, equals congruent to 0? What can you tell me about Q in this case? The Q, the 12 is divisible, I think. But it's English question, so I'm not sure. We want to say that 12 is divisible by Q, and Q is a prime. So what can you tell me about Q in this case? It could be either, Q will be either 2 or 3, because that's the only primes that divide 12. But if I pick Q to be 5, it doesn't work. Proof by example, once again. So how many primes do I have such that X equals, that is T of S minus P, which are smaller than 2 to the m, are divided by this prime? From this point, it's, for me at least, it was new material, so and new ideas. So I want to ask, how many bad primes are there that will cause a false positive for these particular numbers? So to understand how likely it is to stumble upon such false positive, we need to understand the prime factorization of X over here. So what are prime factorization? To remind you all, I can take any number, 12 for example, and write it as 1 prime times another prime, times another prime, times another prime, until you get this number. And obviously this factorization is unique to the order that you're doing it. And if you are using the same number more than once, then you can write it as a prime to the power of something, exponent of something, times another prime to the power of something. And this decomposition is unique. Obviously, for the x, the primes that divide it are unique. And take x and divide by the first prime, the smallest prime, you can continue and generate zero sequence. So x can always be written as 1 prime to the power of some exponent times another prime to the power of some exponent. The exponents are all integers, all the way until the last prime. Quick example, 12 equals 2 to the 2 times 3. 900 is 2 to the 2 times 3 to the 2 times 5 to the 2. Check. And 24 is just 1 prime that appears multiple times, appears 10 times.
Isn't EI much larger than 0, not 1?
EI is, no, 1 prime can appear by itself. That's the exponent. The prime should be indeed larger than 2. Excellent point. You see where it's going. But the prime should be, of course, larger than 2. But the exponent here, when I write 12, 3 appears once. So E1 is, 1 is fine. And each one of the PIs are larger than 2. Only primes that are larger than 2 are in the game. So now let's put this fact together. X calls me a false positive. X modulo Q gave me a false positive, meaning it's divided by one of the bad primes with respect to this X, or with respect to this theory. How many primes participate in the prime decomposition of X? Well, X, we already established it, X only have m bits, so X is smaller than this number. It's most 2 to the n minus 1. Now, I write X in this way. Each PI is either 2 or larger than 2. It's 2 to the power of something. If it appears more than once, better for me. But if X is 1024, it just means there is only 1 prime that divides this number. So if I pick Q at random, it's even less likely that it happens to be 2. The more primes that participate in this decomposition, the more likely it is for me to pick, by mistake, a wrong one, which will cause the module to be 0, which will cause false positive. Okay, so how many primes can I have? What is the largest value of k that I might generate, since each prime is larger than 2? And the exponents only help me. Then k here is, sorry, then k is not larger than n. Then I cannot have more than m bit. If I look at how many bits there are in the pattern, the number of primes that cause the false positive, is smaller than the number of bits that participate in the pattern. Okay, everybody is cool with this observation? It's important for where it's going. So I'll describe the algorithm like as if I'm really performing all these operations. We will actually replace the first part with a much simpler part. So as our next attempt, let's generate a set that, to be consistent with the book, I'll use capital prime to denote this set. And this set contains a lot of primes, 2 times n times m many primes. And each one of them is a relatively small prime. Small, like less than 2 to the 60. Small than log of x. Presumably you can store M and N in your memory, meaning that you can give an address to each character of there, meaning that it's less than 2 to the length of the text is less than 2 to the 64. In other words, you can, each prime here is something that you can store in your computer world, in a single computer world. Okay, so imagine that I create such a set of primes. Well, what I'll replace it with, just a promo, what I'll replace it with is just pick a number or a prime at random, and with good chance it will do just well. But to understand why the algorithm works, we need to think about conceptually this set pi that will include, say, 2, includes 3, 5, 11, Pj, Q, J, QL, running out of indices, but pi is a set of again, when I'm going to go with this is that I'm going to pick a prime out of pi. And all the primes are primes that I'm willing to work with. Don't have too many bits. And again, where it's going to be practically, since I'm just picking the prime at random, I might as well think about a database of primes and just say that's the largest prime that I'm willing to work with. Or I'll pick a number at random and check if this number is prime or not. That's another way to approach it, instead of actually having to have in my computer all this list of primes. But for the analysis, let's assume that I actually took my time and created pi explicitly. And now from prime, I pick from pi, I pick a prime q at random, and I run my algorithm. And I ask, when I'm picking q at random, how many false positive could I have, might happen? And possibly the answer is many. Maybe the input is designed so viciously such that there are a lot of false positives. But actually what I want to, and in this case probably you want to just repeat the experiment and pick another prime. You see that it takes too much, something bad with your data. Not bad, but there is some structures that you didn't notice. Just pick another prime. What I want to say is that there is a 50% chance that your prime will work very well. Will not have any false positive. Again, there is a 50% chance that your prime will not have any false positive. Why this? And the 2 right here is important. That will be where the proof is getting. So I'm looking at t of 0, the window where it was original. T of 0 is a number, very large number, but it's a number. P is a number that's going to be the state. P, I remind you, is just a number that capital P, the string, represents. It's a binary number. So t of 0 minus p, if it is divisible, if this number modulo q is 0, I'm in trouble. It's a false positive. Assuming, of course, that this is not a match, then it will be a false positive if I pick the q that divides it. So how many primes participates in the prime decomposition of this number? I look at the prime decomposition of this number. Of course, I don't do it algorithmically, just as part of the proof. I look at the prime decomposition of this number. How many primes participate in this number, in the prime decomposition? At most n. We saw it in the previous slide. There are k primes that participate in this number, and k is less than n. Again, why? Because each one of the prime is 2, and the maximum value of this number is 2 to the n. So I cannot have more than m primes, each one is larger than 2, whose product generates this number. So I'm looking at T of S minus 1, and I'll say here are the primes, bed primes for T0. I just marked the primes that are bed primes for T0. See how did I for the proof I switch the rules. I said I first generated all these numbers and then I pick Q. That's not how the algorithm works, but conceptually let's assume that I'm doing it. I generated all these numbers and then I pick Q at random. So here are all the primes that participate in the prime decomposition of T of S minus P. And we said that there are at most m guys here that I just marked in red. Similarly, I'll move to T1. The next, shifted the ring a bit. Here are the bed primes. Bed for T of T. Sorry, this was Z for T1 minus P, and here I forgot the T0 minus P. T1 minus P. If we divide this number, so modulo it will be 0, that is T of 0 mod Q would be equal to P mod Q, false positive. Right. So I marked another m bed primes that I prefer not to use. Some of them I might have seen already. And it's at most m because in the prime decomposition, maybe the same prime appeared more than once, like divisible by 4. And maybe it has some overlap with the previous set, maybe not. And I'll go and mark, do another shift, mark another subset. I think that you see where it's going. Another set of at most m, which are bed for T of I minus P for some value I, and in this way I generate all the set of bed primes. How many bed primes did we mark like specified in the union of these sets, taking all the bed primes for any particular shift. Each one of them contains only m bed ones. Each shift contains only m bed primes. How many shifts do I have? N minus m actually, but let's say I called it n bed shifts. So altogether, how many bed shifts? Answer is small or equal than m times n. Each set here is of size m. Each set here is of size m, and I looked at n such sets, size at most n. And obviously there might be overlaps between the sets. That's quite likely. I don't care. In the worst case, that's the number of bed primes that I have. How large is pi? Pi is 2 times mn. Meaning that now when I pick a prime at random, it has a chance of 50% that the prime that I picked doesn't appear in any of the sets, which implies no false positive at all. Cool or cool? So if I pick my prime at random, we have a probability which is large or equal than at least half then I don't have bad primes at all. Okay. So how do we know that pi exists? Let's just skim through it quite fast. How do we choose a random prime in or linear time? The good news is that if you ask how many primes are there as a function of n, as a function of capital N in this case, there is a lot of primes. So remember, I want all my primes to have only m many bits. I want all my primes to be relatively small, at least to fit one computer world. But there is so many primes that it's not hard to generate many of them. Easy to prove that the density of the primes, so there is a lot and lot of primes. And if I'll just pick n to be 9 times m, then the number of primes that I have between 1 to this number, it's large enough. So I can pick, if I'll pick a number at random, from the set and check if it's prime until I'll find a prime, then I'll find a prime quite fast. Since there are so many primes, if you just pick a number at random, don't use any other algorithm, just pick a number at random, ask is this prime or not a prime, and finding if a number of prime or not is, well, your credit card depends on it, and yes, there are algorithms that do factorization relatively fast. Or look at a data structure or a database of primes or do the following. Anyway, just pick at random. And practically what do? You pick a prime at random. The larger the better, but should still fit your computer world, should be smaller than m, should have at most n many bits. Most primes will do it, and they are, just try it. If it works for your data, great. If not, maybe there is something strange in your data, and just pick one again. How many times does it take until you find a prime that doesn't have any false positive? Well, you can either insist on that you can either understand it as there is very low probability that you have good chance of no false positive at all, or you can understand it as it's quite unlikely that you'll have a lot of false positives for one particular prime. So if for every false positive you spend the time to check each element individually, you're good. Understand it either way. Anyway, cool, no? By the way, this paper appeared in the beginning of the 80s, kind of introduced the idea of randomized algorithm, and in the same paper they also discussed an early version of the algorithm of the closest pair between 2 points. So they were two classical problems. Let's talk a bit about the midterm. I'll give you a few questions that I give repeatedly almost every semester, and let's, if you didn't find it already, this question in multiple variants I ask in every semester, which is you have a lot of files and find if any two are identical. I like this question. I use it for many years. I use multiple versions of it, and let's play it. Yes, sir. Still about it. Go ahead.
It's about the midterm in general. If you'd like to finish first, I can hold up.
Basically, that's a question. So I was thinking.
Sure. Just to get some more input from the class, I think opening up the discussion to what's the homework schedule looking like? Because I know that my desire to not push it forward is so that we can have more time to review via the homework material for the final. But of course, the conflicting interest is more time to review for the midterm itself. So basically, I'd like to have it sooner so we can have more homeworks between now and the final. If we push it later, are we going to have like a midterm review homework, or are we going to have another homework, or what's the plan?
I publish a few review questions what I do to the time of the meter does not affect the time. It's just more time to, the material for the midterm is the same. It would be everything until hashing. So it's just to have a bit more questions, more time for us to discuss questions. That's essentially the only reasons maybe to give it a bit different. That's the only parameter that is different between doing it now or doing it next Wednesday. And then next Monday will be fully reviewed. But as far as materials, homework, it will be the same. I will not have time, no matter when I publish homework 4, I will not have time to grade and publish the solutions, and I will not try to force people. I mean, the questions will be relevant to the midterm, but you will not see the solutions, at least there are. For most questions, you will not see the solution. Sometimes I'm giving up the solution that immediately just as, why not? We all share the same desire of, getting you, there is no attempt to sabotage your career completely. So material homework, everything will stay the same no matter what the meter. I will not add more. If I were moving it, I will not add more material to the meter. Obviously. So if it will cause people to change your mind, we can continue on Piazza and let it sink. And for my side, I really don't care. Just asking what's the best for you. Yeah, you have a lot of files. I at least have various copies of the same file that I gave with different names, different directory, different, etc. You want to write a function that will tell you here are two identical files. And naive algorithm, not disjoint from Rabin, naive algorithm would be check every two files, take every bit on the files, and check if they fit. And various obvious heuristics, if the files don't have the same length, let's make sure that they all have same length, size, sum of ASCII characters, if I'm using ASCII characters. Why do I say that they all have the sum of ASCII characters? Because people tend to think about, let's sum up the ASCII values of all the characters in the file, if it's document or image, and that's not a good hash function, so I'll put it out of the discussion immediately. It's not a terrible heuristic, but as a hash function, it's you can do better. So yeah, how should we do it? Again, slow algorithm, check every two files, and if you suspect that they are similar, they pass your, say, the obvious sanity check filtering. They do have they look like they might be. At some point, you need to check each character independently. Do they fit or not? And file is a big thing, so it's expensive operation. You cannot avoid it completely, but I mean, you cannot avoid it completely, but you want to make sure that it happens with low probability, that false positives are rare. They don't happen frequently. So not too hard to think about, but somebody should vocalize it.
Can we just hash?
Yeah, obviously it will start by some hashing of each file and comparing the hash value of the files. Not too hard. And in this part, to make it a full answer in the meter, definitely if it's in the homework, then I want to know which hash function are you using. So which hash function are you using? Files are a big thing. Multiple answers, obviously, but yes.
Dot product, and you can do round robin?
Yeah, dot product is nice, is round robin, and dot product allows you to make one pass of the file. If the file is too large to fit your cache, it just requires one pass. Again, it's not the fastest. You take some constant A1 times a C1. C1 is the first character of the file, plus A2 times C2 plus A3 times C3, and then all these numbers A1, A2, and A3 are constant that you pick according to the algorithm of the dot product. They are all numbers between 0 and the character size that you're using. Like whatever M that you're using, you're going to do everything modulo M. Just like in the algorithm of the dot product, you want the characters, each character of the file to be not more than M. So every AI and every CI, and the A and the CIs are pieces of the file, characters of the file. The reason that it's character, but not necessarily ASCII character. Maybe you want to work where every character is actually a run of 32 bits. Why not? It will be more efficient. It will be just fine. Just make sure that it's still smaller than M. So the primes that you compute the modulo of all of them should be larger than every CI and should be larger than every constant AI that you're going to pick. And these AIs that you pick are also from this range. And at this point, I just used 3 characters, and I get a bit tired of using too many of these AIs, so I'll go back to A1 times C4 plus A2 times C5 plus dot dot dot. If you just do a round robin, probably you want a longer round robin, and all of it do modulo M. And now you store them in a hash table, and then it's easy to check for collisions. If you have collisions of the hash value, then you're happy. You're saying it's a good match. And again, there is plenty of hash functions that are out there, and you can. I had questions about the homework. Can I use various other ones? And sometimes yes, sometimes no, depending what I want to highlight and what can you tell me about this other hash function if you don't know. Let me show you the just typical mistakes that I see about variants of these questions. A typical mistake is to say I'm just using multiplication function. I'll take the whole file and multiply by one big constant. Not terrible, but not really a constant time and not really one pass of the file in the case. And it's too similar to sum up values. So it's not convenient. If the constant is too small, then it's single constant is not great. I can elaborate if you want, but it's and it's not necessarily a constant time from the same reason that we didn't like it in Rabin, that we might end up with a number that is more than n larger bit. That's our one typical mistake. Typical mistake is not specifying what is a hash function at all. Just say we'll hash it somehow. Next, you want to tell me just, maybe not you, but when I'm giving it 445, I'll ask for an answer that specifies which hash function you're using. You're using, say, open addressing. But if n is a number of files, then I want the table to be twice as large. So the size of the table should be twice as large, or else insertion takes more than a constant time, and find takes more than a constant time. We played last meeting with the probabilities that you need more than one probe. Like what the probability is that you need I probes until you find what you're searching. So if they don't tell me the hash table at all. But now we are getting into more subtle errors about this question. So I have this hash function, hash of the file. Maybe it's dot product. Sometimes people suggest, and since it happens more than once, I thought that it's a good idea. So I can also use your operating system suggests a few protocols that sometimes are stored in the file. One of them is called MD5. If you ask what is the MD5 of one of your file, it will run a hashing algorithm and returns a hash value. Not bad so far. And then people, since I know that it's a typical mistake, I'm asking about it. What do I do with this hash value? And people will say, I'll store file 1, store file 1, or link to file 1. So file 1 in the table at index MD5 of file 1. So I'll take this hash value, not bad so far, and use it as an index in the table. Not hard to see what's the issue. Somebody please vocalize.
You don't know the range of the MD5 values?
Yeah, that when our discussion is somehow confusing two different usage of the hash function. Once we want to think about it as a short index or short signature of the file, and it has a nice property that there are no false negative. If I have two files that are, if the hash values of two files are different, then these files are different, no question. But if they are similar, then there is good probability that they do meet. So you want a hash function that is good hash function and returns a value that is hopefully large for every file. So you have different gaps. Of course, the larger the signature, the more discrepancies are between the different files. Less chance of false positive. But taking a too large signature doesn't mean that you can use it as an index in the file. But this now, MD5 in particular, returns a string of 256 characters, that's the value of MD5, and I don't know computers that can store this value directly. Does it mean not to use it? No, it's a great hash function. Just don't use this as your hash, as an index. You need now to have another hash function, h over here, that you will take the signature, that's the signature of the file, and make it into an index. And now it's all good. And obviously you see the algorithm that comes from it. If I have two files, I'll use chain hashing just because it's easier to visualize it. If I have two files that hit in the table cell I have two files, or I find two entries that hit cell I in the hash table, then what should I do? The algorithm, what should I do? Well, I need to check if they are identical, but now this algorithm suggests two steps. If they hit index I, that is the age of the MD5, is identical, then I ask if the MD5 is identical. And only if the MD5 is identical, then I go to check them character by character. Or you can play with various levels of this hierarchy if you want. Everybody understand? There is one hash file that fits to use as an index, and one that really is the signature of the number. Here's another question that I've learned. I have to remove it from the homework. So we have 2 minutes. I'll say sometimes I do for image a very simple white balancing, which means every character is a number. So in the file I'll take C, and in one file I'll take C and multiply it by alpha. I take the first character, multiply by alpha. I take the second character, multiply by alpha, and so on, but by the same alpha. All the characters of the file, Cn, are moving to alpha Cn. Do like white balancing. Somebody stole your image and try to cause your simple copyright check to see if the image appear or not appear. So somebody took your image and went to Photoshop and changed the white balance by multiply everything by a constant. So you have two files, one when I multiplied everything by alpha, one when I didn't, but I still want to think about them as identical. There's now two files are identical if one is obtained from the other by multiply by a constant. What do I do with the hash function now? What's my algorithm now? The goal is the same, find identical files. By the way, I plan to continue a bit as long as there is students. Going into my office hours, but as long as I can think of question or you have questions, we can continue. But at least let's nail this question. Everybody understand? I have a lot of files, and in some place on my file system or in the internet, I find my file once multiplied by a constant, and another place I found the same file multiplied by a different constant, and I don't know what are these constants. But I still want to think about the files as identical. Many solutions, but
You're going to want to move your hash to the canonical form for hashing.
exactly. I'll decide. For when I asked you in question 13, that was a hint to everything, that you store strings. You store, the example was low versus low. Each student that I ever had realized, yes, I need to decide that I always store it as small letters, or always store it as larger letters. But one of the two. So that was the canonical form. So then we move to rotation, and we decide that the canonical form is the one that lexicographically is the smallest in my game when I rotate it. Here in the file, just much more practical. What do? I decide that I always take the file and move to some canonical form. You decide what is a canonical form. You can decide that I'll move it so the first character is always 1. Divide all the characters, all the pixels, by the value of the first pixel. And then even if I multiply by 1, it's still the same. But it will be transferred to the same file. And then if I hash them, they'll be identical after this transformation. In other exams, I ask similar questions where I'll say they have a set of points, x, y, and I'll say the 2 points are identical if, when you looked exactly into the question tried to mislead you a bit, but if you look well into the question, 2 points are identical if there is a line that goes through both of them. So you have a lot of points stored in the memory of your computer. Tell me if there are 2 identical ones, and 2 identical ones here means that there is a line that starts at the origin at 0, 0, and go through the first and go through the second. And the direction is, of course, to canonize, which will be how? I give you a number x, y. I'll try to give you a number x, y. And I want to decide what is the canonical form of this number. Yeah.
Y over x?
Yeah. Compute y over x, that's just the arctangent of the tangent of this ratio of the point. So 2 points of the same line will have the same value of y over x, which is identical to take the file that we had before that and move the first number into x over x and take the second number in and move it into y over x. All you did is taking all the points along the line and shift all of them to this point. So of course, you don't know what is this line ahead of time, but once you're doing this transformation, then 2 identical points will be mapped into the same value. Modulo numerical issues, numerical errors, you'll get to the same value, and then the hash function of both of them will be the same. A question, open-ended question that I asked at some point said, you want to do face recognition, or you want to understand how the bad guys are doing face recognition, getting into politics now, and the way that your algorithm will work is that you take an image of a person from the front, a photo image, a passport image, and you have one detector. You have a detector that says in this person, here is the lowest point of the face. Lower point of the nose. And I'll show you these coordinates of them. I mean, we're not making it into a vision course, but you have a piece of code that tells you where in the image which pixel the lower post of the nose is. And will tell you similarly a different detector will specify where is the highest point. Different detector will tell you what's the difference between the eyes and so on. There are several few detectors. And now I have different pictures of the same person, and the picture are different by, say, translation and rotation. That is, the person before the camera just moved a bit or moved a bit forward, closer and further. For rotation, for whichever. You want for transformation, and now I'll ask you, given this set of transformation, find a canonical way that you'll represent the images, these coordinates, and then once you have this canonical part, you can hash it. And that's one of the classical ways that face recognition will work. You hash it, and then a new person comes, and you can quickly realize if this person, even though the camera is a bit further or closer to the person, if this person appears in your database or not. So, based on this part. I mean, it was not a correct, incorrect, but I wanted to see if people understand that this canonical way appears. So that was a few typical questions. Another typical question about a skip list that I think that I didn't ask you is that, hopefully you all remember what is a perfect hashing, what is a perfect skip list. Perfect skip list, you're looking at all the elements at the lowermost level. Look at all the elements in the lowermost level, and you're going upgrade, don't upgrade, upgrade, don't upgrade, upgrade, don't upgrade, and then half of the elements are being promoted. And that's how you are creating the second level and continue till you're running out of elements. Let's change this behavior a bit. Let's decide that I'll decide upgrade, don't. So yes, no, no, yes, no, no, yes, no, no, and yes, no, no. That is upgrade, don't, upgrade, don't, upgrade, don't, and so on. So every third element is being upgraded, and I repeat it for the following part. And I'll ask what happens to the number of levels. What happens? How many levels do I have? I'll have few, but I'll ask you exactly how many. That's it. If I'll make these skips, so I'll skip over D elements instead of, that is not yes, no, but these 17, then yes, and then 17 elements no. Upgrade, wait 17 elements. And the way that once you're done generating the second level, you're moving to generate the next one. So if I have these big gaps of D elements that I skip, how many levels do I have?
D base N.
It's log of D to the base A. No much argument about it. Now, log, if D is larger, it means that I have fewer levels. What happens to the search time in the skip list? Higher, lower, comparing to the perfect skip list, original. Yeah, let's. Other question. I mean, it's tempting to think that I have fewer levels, and the number of, and I need to spend a constant time in each level. So it seems like that. And by the way, where I'm going with this question is that usually we don't have a perfect skip list, but we are tossing a coin, and this coin is, the way I presented this algorithm, this coin is 50-50. Whatever if I decide that my coin has only 10% of going up and 90% of don't be promoted, will it make my skip list faster or slower? and the proof coming from here. And let's take a vote. How many people think that it's not fair because I gave it up. So the search time will be slower in this case. But one example, one intuition about it is that, just as an intuition, if D is huge, then it's almost a linear list, if you wish to say. If D is n, just as to show you that why the time is. But what is actually the time if I have this D perfect skip list? Then indeed that I have log D levels, but what's the worst case? Why is this taking more time if D is large? It's true that I have fewer levels, but inside every level, I have to scan up to D minus 1 many elements in the worst case. So the query time is actually D times log of D of n. And when D becomes larger, then of course, when D becomes larger, then the log goes down, but the D is more dominant. So it increases the running time. Now, a question that appeared like 5 times across the course, check it out in this case, like using this D, what is the memory? How many cells do you have? You answered it when D was 2, that is our second level, but if D is not 2, how much memory do I need? How many cells do I have? Maybe I don't see. Kind of, maybe you're right. I don't remember it by heart, so I think, but how do I do it?
It's going to be a logarithmic something at each level.
I don't, I'll do the standard trick that I'll avoid any logarithm. Every sum that I see, I will always try to continue to infinity. There was only one sum in this class where we didn't go to infinity, where it was actually important to stop at the nth element. I'll remind, if I don't get back to it in the next question, I'll remind you there was, or think in the meantime, what was the sum that we really cared about to stop. But all the other sums, we always try to go to infinity. So let's ask. N times our standard trick. Level, in the lowermost level, I'm spending 1 times n. Every element appears in level 1. Level 2, 1 over D, whatever D is. That's it. Next, it would be 1 over D squared plus dot dot dot, let it runs to infinity. And I do expect everybody here to realize that this sum is 1 over 1 minus alpha, 1 minus alpha, if this is alpha, 1 over 1 over D, and it might turn out that you're actually right when I finish rearranging it. So that's the overall memory. And that's also the expected memory that I'm going to waste if I am using an unfair coin that has only D chance to positive. A harder question is if I ask you what the probability of seeing a skip list whose height is more than 10, but your probability to see a bad skip list where bad would be more than 10 times log D. So I probably will not ask you to give the whole proof, but I can ask you to prove part of it, because we did spend an hour and something hitting the question of what is the question of what the probability of seeing a skip list whose height is more than Z log n. So log n would be the expected value. What's the chance of seeing something that is 3 times more than expected, 10 times more than expected? We spend lots of time handling this question for a fair skip list. So if I ask something about it, it will be to see did you actually went over this proof or not. Yeah, which sum do we really care where do we stop? It's not I will not use it in the exam, this statement. But I might ask about this sum.
Sum? Is it the harmonic sum?
The harmonic sum. A few times, remember we had a little function that picked random numbers and updated the maximum. I picked a random number and updated the maximum. Or I generated a random permutation of keys and updated the maximum. And I asked how many times does it happen, and we said that I'll update the maximum definitely on my first step. Now, when I'm adding one number, the chance that it's larger than the maximum is half. Because of backward analysis, you have two elements, what's the chance that the last one is larger than the previous two? If all permutations are the same, it's half. Next one, if you have three elements, the chance that you update the maximum is third, because when you are generating three elements x, y, z, you already decided about them, but all permutations are equally, has the same probability. One of these elements is the largest one. What's the chance that it's the last one? It's the same chance that it's in the middle, or the same chance that it's in the leftmost. And so on. And this sum, we continue until 1 over n. And if we would go all the way to infinity, it will end in infinity, this sum. But beside it, the sum is more or less the integral of 1 over x dx, where x goes from 1 till n with a bit noise, which is nothing but ln n. Don't forget backward analysis. The question about finding the triangle with minimum perimeter that you have in homework 3, quick answer is that some people try to repeat the algorithm, making sure that in the grid I have only 1 point in every grid cell, which would be nice if I have only 1 point in every grid cell, but then if I'm getting another point, and that might participate in the smallest triangle, smallest perimeter triangle, but might be very, very many grid cells far away from this one. So the invariant that is much easier to decide upon is that I'll have the smallest perimeter triangle that I've seen so far. That is, its perimeter is P for perimeter, the sum of the lengths of all the edges. And now I'll decide that the grid cell is, say, both sides, P over 4, which implies that I cannot have 3 vertices in the same cell, but possibly I have 2. And if you're making sure that there are 2, then everything else in the algorithm stays the same. You don't need to look too many grid cells out of there. And if you have a new query point or new PI, then you're checking 1 grid cells and other grid cells that are 1 or 2 hops away, and you can easily prove that you don't need to check any point that is more than 2 hops away, because any triangle that it participates in will generate a too large triangle. Here is an exam question that's homework 4 question from the draft. But what's the probability when I create? I ran the algorithm for creating a perfect hash function. What's the probability that the size is more than linear? If I ran the whole algorithm, it's a bit of a trap question. It's not fair, but at least it's good to bring this point up. What's the probability that I need more than linear time to when the algorithm terminates? The reason that it's a trap question is that it asks on things that you do know and you do remember, but you might have forgotten that the algorithm said, I'll check the quality of each function that I'm going to use. And I'll go over the perfect hash function if anybody wants, but every time that I'm generating my first hash function in my first table, I'm asking, does it do a good job? Because it has a probability of half to do a good job. What is a good job? Look at how many elements are mapped to this cell, how many elements are mapped into this cell, and how many elements are mapped to this cell. And what did the algorithm tell you? The algorithm says you have n1, n2, n many elements that the hash function mapped. And you look at the number sigma of ni squared, the sum of the square of all the elements, and we have a good probability of half, that this number is order f, which, because it's universal family of hash function, and we played with this, that was a sum of squares, because for each element, it has probability of half to meet every other element. But the algorithm also includes another part. If this doesn't happen, then pick another hash function. And if it doesn't happen, pick another one, and so on. And then you have to pick good hash functions to each subset individually. But then these ones you picked as quadratic space, but quadratic in what? Quadratic in the elements of numbers that appears here. Quadratic in the elements that appears here, and so on. So since you already passed this stage, then you know that that's a non-issue. But you now, for the perfect, you have to check something else when you're generating these new tables. We're going to need to check when I mapped all these keys to this new table that I don't have any collisions, which I have good chance, but I want it to be perfect, maybe no collisions at all. I have to check that for this subset, when I take, again, because there is probability of half that it's satisfied, then if I do have collisions for this table by itself, I'll just pick a new table for this part. Try again. And try again, and because the probability is half, the expected number of tries until you hit a good one is only a constant. And then you are moving to the next subset, the next subset, the next subset, and so on. Is this clear, or should I go revise it with more details?
Are you going to ask something like this in the midterm? Because just to explain all that stuff in the midterm going to take a lot of time for this single question, for example.
The reason that I probably wouldn't ask it is that it feels a bit unfair. Like, you could have understood 95% of the core and just was blinking when I said, if it doesn't work on the first try, I'll try again. Now, you're asking, do I feel fair to ask it? Now I do. So, but originally I would think that it's not a topic, it's a nasty question. But to ask you why, if I take this function, here is a first a part that I can ask. Pick a hash function, you have n keys, and pick a table from a universal family, pick a table of size n squared, which we did do. How many collisions do you expect to find among the whole set? And we want to say if it's n squared, then with probability half, there are no collisions at all. So there is a good chance that there are no collisions, but to ask why, I might ask. It's not a great question, but at least did you go over? I'll ask something that will be hard to cut and paste from the textbook, but I'll not ask it in this part, so I'll try to distinguish between cut and paste answer versus did you understand the proof or not. Okay. What else? The quick sort that we spent tons of time. We went through a few stages to prove that quick sort goes in n log n. Started, remember all the proofs? We started from a simple proof about good pivot versus bad pivot. You have a 80% chance to get a good pivot. Don't forget why. I can easily come up with many questions that will use good pivot in other parts. You had one of them in the homework where instead of doing quicksort, you build a binary tree by inserting elements, but the whole mechanism of good pivot, bad pivot was going word by word. So, and remember when we analyzed quicksort, we had a few steps, and one was let's look at good pivot. That there is 80% chance to find a good pivot. What is good pivot? A key that is not in the 10%, that is the smallest one, not in the 10% of the bigger one. And then the proof went by saying you have 80%, look at the set of keys that you are going to sort right now in this stage of the sorting, and you have 80% chance to pick an element in the middle 80%. That. And if it does happen, if all your choices are good, then your tree will still have logarithmic height, not log to the base 2, log to the base of smaller number, because it might be that a lot of the elements are here and only 10% are on the other side. But a constant fraction will split into each side of the recursion. So that was one proof. If you don't remember it, ask, or I can go over it, or at least revise it. And the more subtle proof, but harder one, was really going over the backward analysis once again. I looked at two elements, I and j, asked what the probability is that they'll ever be compared. When will this element I and j will be compared? They'll be compared if among the set of I, j, and everything in between, the first element that I picked is I, and then it will be compared to j. As first element that I picked as a pivot was I, and then it will be compared to j. Or the first element that I picked as a pivot was j, and then it will be compared to I. In these two cases, I will compare them. If I picked an element which is between I and j, then they are going into different slides, and I will not compare them. So we asked, what's the probability that I and j will be compared? It depends how many keys are there between them. That's the only parameter that determines it. Since I pick a pivot uniformly at each stage. You look puzzled. Should I go over the proof? Yeah. So yeah. And then we had this double sum. Then we had this double sum where essentially we asked what is the sum of 2 divided by j minus I plus 1. Where does this number is coming from? J minus I plus 1, because I was running through all the ij. I'm really scanning through it very quickly. I was running through all the elements, all pairs of elements. Here is I, here is j. I assume that they are already sorted. And this number over here is just how many elements are there among them. That I plus 1, I plus 2, all the way to j. This is how many elements you have between j to I. What are the bad choices that will cause I to be compared to j? It will happen if and only if the first one that I picked is either this one or this one. That's why it's 2 over here, sum up into this sum, and I think that I didn't go through the whole procedure. I just said, for a fixed difference of I and j, this element will appear at most n times. For a fixed value of this element will appear n times, and the different values that I have over here are exactly, we have 1, 3, 2 times, and so on, all the way up to 1 over n, which give me a really tight boundary, n to n ln n, which is actually very close to that one. So that was the rigorous part. If you remember all of it, great. If you don't remember, at least remember all the details about the good pivot, bad pivot, and why good pivots are sufficient. Okay, I'm not entirely sure about my weekend plans. There's some family commitments, but when I'm in town, I'll definitely make myself available for questions. I didn't see too much stress to move it. I'll let you meditate on it, but if nobody will say, yes, please move the meter. If I wouldn't see a few students saying, yes, we really want, we are staying with the same date, the same everything. For my format is, some of you took my courses, we'll have 5, 6 questions, you have to answer like 4 out of the 6. Not necessarily with the same grade. If you're getting more than 100, good for you. It stores and used later for class participation. It's always out of 100. Yeah, I don't know. Zoom people, any questions? Okay. Okay. Thanks. Yeah, and it'll definitely be available like a Zoom or live on Friday.